All right, now we're live, finally.
Okay.
All right, welcome everyone. Thank you for coming today. We have this rare opportunity of having Stefanos visiting from Canada, so it's a great pleasure to have him with us today. Stefanos is the ultimate Renaissance man. He can tell you about strongly correlated systems, X-ray spectroscopies, Qubits, quantum computing, complex systems. I mean, he's done all of that. And today he's going to give us an overview of his recent work on some of actual experiments on a quantum simulator, right? And non-equilibrium phase transitions. Stefanos, please take it away.
Okay. Yeah, thanks for the introduction. Thank you for having me here. Thank you for showing up. Today I'm going to talk to you about some theoretical and experimental work that we did, where we attempt to use the existing quantum devices to do something useful, right? Some useful physics. So just to preface a bit this work, so you probably have heard that companies like IBM, Honeywell, Google, etc., they are now producing these devices that assemble arrays of qubits on which we can do operations that entangle the qubits. And even though we cannot do error correction, we have these noisy qubits, and we are trying to do something useful with them. Now the problem is that these devices are really limited, and so what you can do with them is also limited. And so today I would like to show you a case where we were able to do something useful. And I will explain the specific context in which our work falls into. So this is work I did my student Jeremy, who is also a nice comic designer. So you can check his webcomic at that address. Okay, so here's the outline for this talk. I will first talk about partial measurement of multi-qubit quantum states. We'll be interested in highly entangled states, volume law entangled states, and then measuring the qubits in these states and ask what happens to the entanglement as we measure. This is motivated, from the fundamental point of view. We just want to know what behaviors are possible, and secondly, from the recent field of monitored quantum circuits and measurement-induced phase transitions. And so I'll juxtapose what we're doing with what's going on in that field. Then I will show you specifically what kind of states we will be preparing. And specifically, these are states associated to classical spin glass models called p-spin models. Okay, and then I will show you the circuits that actually generate these states. And then I will show you the theory that describes the entanglement in these states. And finally, I will show you some experimental results that we obtained from the IBM quantum computers. Okay, so the take-home message of this talk can be explained really simply. And so even if the rest of the talk is, unclear or not well delivered, I think this part will capture the essence. Okay, so let's imagine that we have prepared n bell pairs, as I show here, and we are interested in arranging them in this fashion such that the left part of each is in subsystem A on the left side, and the right side of each bell pair is in subsystem B. And now we want to ask, what is the entanglement across this cut that separates subsystems A and B? Okay. Entanglement can be quantified using the entanglement entropy, and this is the formula. we're interested in the behavior of this quantity as we measure the qubits on subsystem A one by one. Okay, so let's try and plot entanglement entropy versus the number of qubits that we have measured on this side. So first, let's consider the n bell pairs without measuring anything. Okay, so we know that each bell pair contributes 1 bit of entanglement, right? And so here, when I have measured nothing, I get an entanglement entropy equal to n, modulo some factor. Okay, now suppose we measure the first qubit in subsystem A. What will happen? Well, we will collapse the first bell pair. Now this is in a classical state. Okay. And what has happened here in terms of entanglement entropies, we have lost 1 bit of entanglement. Okay. Easy peasy. Now let's do it with the second qubit in subsystem A. What will happen? Well, same thing. We'll lose another bit of entanglement. And now let's keep going. Eventually, what will happen is, after we measure the nth qubit, we have collapsed all of our n bell pairs, and we have a classical configuration and no entanglement. Okay. So this state, the initial state that we had, was a highly entangled volume law state with respect to this cut, right? And we progressively measured the qubits, and what we got was a curve that looks like this. It's just a very simple curve, just a linear function, and nothing special happened. So now we can ask the question, do all volume law, generic volume law states behave the same way as this? And the answer that I want to give is that actually there exist ensembles of volume law states that exhibit a very different behavior, namely a behavior where, as a function of the fraction of qubits measured, you will start with a decay like the one that I showed you, but there will be a critical fraction beyond which this behavior of the entanglement entropy will change. And in fact, this point here will have the characteristics of an actual critical point. Okay, so in this sense, I will be talking about criticality of entanglement or entanglement criticality. Okay. Okay, so that's the whole story in 2 slides. Okay, this is what this talk is about. Now, why are we interested in talking about this sort of thing? First of all, okay, from the fundamental point of view, we want to understand what happens as we measure qubits that are at the output of our quantum circuit. And a relevant topic is the topic of monitored quantum circuits, where now we imagine we start from some initial state that we're evolving with some unitary circuit, but this unitary circuit is implemented with hardware that is decoherent. Okay? And so how do we model this decoherence? Well, we imagine, to 0th order, projective measurement events that happen at a certain rate. Okay, and then we ask, okay, suppose this circuit initially starts from a product state and is supposed to generate some long range or volume law entangled state at some point. So that's the perfect circuit. How does this picture change if the qubits are decoherent? Yeah, at a certain rate. Clearly, if that rate is too high, say all of the qubits decohere all of the time, you will never build any entanglement. Okay, so you'll start from an area law state, and you'll end up with an area law state. If the rate of measurement is close to 0, it means the circuit is perfect, so you'll end up with a volume law. However, so these are the two, and it turns out that there exists a critical point, a critical rate at which you go from one phase of weak monitoring that produces volume law states to a phase of strong monitoring that produces area. Okay. So this is similar to what I was talking about before, but it's not quite the same because in this case, we're talking about steady state dynamics. So we imagine very long times, and then we are looking for the steady state properties of long times. Whereas what I'll be showing you in this talk is much simpler. I produce a state, given state, and now from that state, I just do measurements of the qubits one by one. So in a sense, here we're talking about a simpler setting, or rather, we imagine measurement events only at the final step.
So there's no Hamiltonian.
There is no Hamiltonian in what we're doing. It's just circuits. So it's all dynamical.
But I mean, these circuits have some sort of unitary time evolution, like imprinted into them.
Yeah. So all of these are unitary.
Okay.
Yeah, these are all gates, and then the only extra ingredient on top of unitarity are these projective events. That's it. Okay. Okay. So what are the fundamental questions that we are interested in? So here we've been talking about the behavior of entanglement as a function of measurements, right? Or collapse events. So quantifying entanglement is tricky, right? So in reality, measuring entanglement entropy is not something that can be done easily on hardware because you need to reproduce the state on your classical computer with tomography and then try to decompose it and Schmidt decompose it and measure the entanglement state. So one question is how to measure entanglement. And I put this on the theoretical side because it's kind of like our job if we make a proposal about this stuff to show that it is somehow the quantity that we want is somehow experimentally accessible. The second thing is, do we have some theory that describes this transition? Is there a well-defined theoretical setting? And moreover, do we have a theory that works directly in the experimental limit? Right? There are other theories for these sort of transitions, especially the monitor quantum circuits that work in unphysical limits. Okay? Here we want to have a theory that's as close to the experimental reality as possible. And then there's other questions more related to practicality. So for example, in many cases, in what I showed you before, these monitor quantum circuits, to actually draw a conclusion as to what happens, you need to reproduce the same measurement record many times in order for your measurements to actually be useful in estimating entanglement. But if you have many of these measurement events in an entangling circuit, getting the same outcome is experimentally improbable. Okay, so this leads to a problem of post-selection. And secondly, okay, is the whole protocol that I'm proposing feasible on hardware, and can I access large enough system sizes? Okay, because we have limited numbers of qubits that are connected a certain way, and these qubits are also noisy. Okay. Okay, so in this talk, I will set out to answer these questions for you. Okay, now, what are the states that we will be building? I mentioned already the p-spin model. So this is a classical spin model. And the way it works is as follows. This is a Hamiltonian, classical Hamiltonian, defined on a graph. Okay? We have a sum of interaction terms here. And each interaction term involves p spins. So in this case, I'm looking at p equals 3. So I have an interaction term that can be ferromagnetic or antiferromagnetic, and this choice is done at random. So I randomly sample these couplings for a given graph. And then I can pictorially represent this Hamiltonian as a bipartite graph where one partition is represents my spins, and the other the interactions. You see here, I have these top vertices here of m interactions over n spins, and each one is connected to 3 spins. Okay. So this is the p-spin model. This is a paradigmatic spin glass model. Okay, and the way you can understand this is, suppose that we impose none of these terms initially. Okay, we have 2 to the n configurations for our spins, and we now start imposing these terms. And so what will happen is, initially, if you include only a few of these terms, you have an under constraint system. So you'll have a bunch of spins. Most of the configurations are allowed. So you have what? A paramagnet. But as you add more and more of these terms, you're constraining the ground state manifold more and more. And in fact, there is a transition to a spin glass that I will show you in a second. Okay. The cool thing about the p-spin models is that we can solve them exactly through this mapping here to Boolean, to a system of equations modulo 2. And the way this works is, I'm showing here, you build what is called the bi-adjacency matrix of this graph, where now each row represents one interaction. So you see here, this interaction is, the first one is connected to spins 1, 2, and 6, and I have the corresponding entries be non-zero in this matrix. Okay, and this matrix is this matrix P here in this equation. So as you also can see here, what is important, where does this modulo 2 come from? Well, you see here, the important thing for the energy is just the parity of a configuration over these qubits, right? So if I have, say, 1, 0, 1 here, or 1, 1, 0, it doesn't make a difference from the energy point of view. So what is important here is the parity. So hence, we have this modulo 2 here. And so, okay, say I add one term here, half of my configurations become excited states, and the other half become ground states. I add a second term, I again divide by 2, my ground states, and then by 2, I divide by 2 every time I add the term. So basically what will happen is, how many ground states will I have? I start with 2 to the n. And then I need to divide a number of times proportional to the number of linearly independent interactions that I have. And the number of linearly independent interactions that I have is simply the rank of this matrix. So I can very easily calculate the number of ground states and correspondingly the ground state entropy of this classical model. Okay. So how does this ground state entropy behave? So if this is the entropy, also any thermodynamic quantity that depends on this entropy behaves accordingly. So how does this behave? As I add more and more interactions, so I increase this number m of interactions over the number of spins. So here it is. We start from a paramagnetic phase where each additional interaction term that I add divides the number of ground states by 2. So I have an entropy that's going linearly down up until a certain point where something changes, and then I obtain a different scaling of the ground state entropy. And basically what is happening here past this point is that the interactions that I add lose linear independence with one another in this matrix P. And so that's why I'm going down all the way to here, and then I'm peeling off. And this is a critical point, okay? And it's a transition between a paramagnet and a spin glass. Okay, so here on this side, here I have, this is a disordered system, there's no order parameter. Here I have a spin glass order parameter that defines this phase. And what is the spin glass order parameter? It's something called an Edwards-Anderson order parameter, which is you take the configurations in the ground state manifold, and you calculate the overlaps between two different ground states, and then you average over them. Okay, so this is called the overlap order parameter. And now the ground state entropy averaged, again, this is a disordered model, so we average over instances, right, over different graphs. The ground state entropy is given by the order parameter, exactly. And then in turn, everything, both the order parameter and the entropy, is given by just the rank of this matrix. And so studying this expression here, which is exact, we can determine the precise critical point, which happens at this value. This is our ratio of the number of interactions over spins. Okay, so I can have more than one. I just keep adding interactions. A ratio of higher than one, I mean. So we have a critical point, and also another thing to consider or to remember is that here we have an exponential number of ground states, and here we also have an exponential number of ground states, both sides. Okay? That will be important later. Okay, so this is the spin glass transition, and because it's a transition to a glass, I call it vitrification, hence the title, the vitrification in the title of the talk. Okay, so I've shown you how the classical system works. Now, how do we implement this in practice? So I already told you that what matters here is parity. And so what I'm going to do here is I'm going to show you how parity circuits work. Okay, so suppose I take a qubit, and each qubit represents a spin for me. Okay, and then I will have an auxiliary qubit here, this Y1, that represents the first interaction term in this instance. So what I want is this qubit to store the parity of each of the configurations of the 6 spins that I have. So how do I do this? Well, that's simple. I want to C naught with the Y qubit as a target, right? And so I C naught for the first interaction, qubits corresponding to spins 1, 2, and 6. So here's how it works. I do a C naught first, followed by a swap. So I hit the qubit x1, okay, C naught it, and then I bring the Y qubit up here, C naught the second qubit, and then bring the Y qubit up here. Then the next qubit I'm touching is the 6th one. So I swap all the way up, okay, and then swap the Y up there. So now I basically transported the Y qubit from here to there. And also now at the output, the Y qubit stores the parity of the rest. Okay? So if I look at the whole circuit, it looks like this. Okay, so in a sense, if you tilt your head and squint, you see that basically this reproduces this matrix here. Okay, so the protocol is as follows. We initialize all the parity qubits, the interaction qubits into the state 0. And we initialize all of the qubits that represent the spins in the plus state so that we have all spin configurations at the input. At the output of the circuit, we will have the following state. We will have, for each configuration Y of the parity qubits, we will have the corresponding configurations of the spin qubits with that parity, Y. Okay? So how many possible such configurations exist? Well, due to the rank B. It's given by the rank of the matrix B. Furthermore, if you look at this state, you see that it's already in Schmidt decomposed form. Okay, so it's already a Schmidt decomposition because each Y is just a bit string and it's orthogonal to all other bit strings. And these X's that are consistent with this Y, they're all orthogonal to one another for a different one, okay, for different Ys. So this is a Schmidt decomposition, so I already know the entanglement entropy of it. Okay, these are the Schmidt coefficients. I can calculate the entanglement already. Okay. Okay, so this is without doing any measurements. So the next step is to see how this behaves upon measurements. So let's take a system where it's not this illustration is not the best, but imagine that I have a lot more parities than I have spins. This guarantees that the rank of this matrix B that describes the whole system is equal to the number n of spins, okay? Because it will be the smaller of the two dimensions of the matrix. And the smaller of the two dimensions is n. Okay, so now what will happen is, at the output here, before I measure anything, I have entanglement entropy equal to n. But now let's start measuring the parity qubits. Each measurement will collapse the spin states to a fixed parity sector. And the more I measure, the fewer states I have. And so how do I decrease the entropy? Well, I start with an entropy proportional to n or equal to n. And I'm subtracting entropy equal to the rank of the submatrix here corresponding to the qubits that I measured. Okay, and the reason is that basically every time I'm measuring one of these qubits, I'm collapsing the state more and more and more. Okay. Okay, but what is this? Well, this is equal to the ground state entropy of my p-spin model for just this part. Okay, I showed you earlier already that it's this, okay, 2 to the n minus rank b. I take the logarithm, and that's it. That's the same here. So here I have a system where, all of this to say, here I have a system where the entanglement entropy is given exactly by the ground state entropy of the spin glass. That's exactly, without any approximation, in the experimental limit. Okay, so there's nothing, I'm not hiding any constants, I'm not doing any extrapolation or anything. Okay, furthermore, I have an analytic form for this, which becomes exact in the thermodynamic limit. And also, as I showed you before, I know that there exists a phase transition for this ground state entropy of the spin glass. And because the ground state entropy of the spin glass and the entanglement entropy in my circuits are one and the same thing, I know that there will be a criticality for the entanglement in the circuit. Okay. I'm going to skip this. So now let's look at the order parameter. Forget about this part here. This just ignore the left part for now. Let's look at the spin glass order parameter, which was this. Remember this overlap between configurations. In the paramagnetic state, this overlap averages to 0 because you get like a random jumble of states. In the spin glass state, it becomes non-zero. Okay. And so here I'm showing experiments. Sorry, this is theory for my circuits. Okay, so I can do these calculations for my circuits just to verify that indeed I get what is expected from the classical theory.
What is the number? The number.
This okay. So
on
this
on
is the
legend.
order parameter as a function of the fraction of qubits measured over spin qubits.
In the legend, the different curves, different colors.
Yeah, sorry. Okay, yeah. So this is the number of qubits. Uniform means that I start with the old class state here. So I have a uniform superposition over configurations.
And exact means what in the
exact is in the thermodynamic limit.
Okay.
So you see, I get the typical thing that I get in around critical points, this sharpening of the curve as I increase the system size. That's what this is supposed to show you. Mm-hmm. Okay. And I'll comment on the red curves later. Yes.
Just wanted to
hopefully draw a connection that is correct. So a few slides back, you had the on the x-axis was the ratio of interactions to spins, and you were showing how the entanglement has that non-analyticity. And so can you remind me where you said that calculation was coming from and then confirm that what's causing the decrease is by changing the ratio?
Yeah.
That's okay.
Yeah. So this is the case.
Yeah, that.
This is the case for the spin glass, which is the number of terms in the Hamiltonian. So this is the number of interaction terms over the number of spins.
So that's coming, this is calculated from just those equations on the right there.
Yes.
Okay. So then.
So in the qubit, sorry, in the just to complete the thought,
Yep, uh-huh.
in the circuit case, now this is number of, remember here I showed you that the part that matters is the part that I measure. Okay. So it's the size of this A part over the size of this part. Like the number of the spins, the number of the interactions measured over the number of spins.
And
so
that's
equivalent.
That was the exact connection I wanted to confirm. So the way you're accomplishing in the circuit case, that plot, that changing of the ratio is by measuring over the parity.
Exactly, because if you measure a parity here and you get, say, outcome 0, what you're saying is that for these qubits 1, 2, and 6, I only accept even parity configurations. So you're enforcing essentially a parity interaction. Okay, for every parity qubit measure. Okay. Okay, so this is how this is expected to work. Okay, now the big question is, does it actually work? So these are experiments that we did on the IBM Q systems. This is from a collection of different machines. Okay, so the data comes from different quantum computers, and we have done some experimental tricks that I'll be happy to explain afterwards, but basically we never did any approximation that is uncontrollable. Okay, everything, any rewriting of circuits that we did was exact. And so here I'm plotting the same plot that I was showing before, an estimated order parameter. It's the same overlap order parameter as I was showing before, but now the averaging is not over the complete ground state manifold because that would take exponential time. Okay, so we sample the ground state manifold and we calculate the order parameter for the sample as a function of this alpha ratio that I was showing before, which is basically number of interactions measured, parities measured versus over a number of qubits, spin qubits. Okay. And now what I want to show is basically the evolution as a function of system size again. And what we see is this sharpening of the curves that resembles what we were supposed to get for a critical point. More importantly, what you see is here the dashed lines are calculations for the corresponding sizes, system sizes that are exact, okay, done on the classical computer. And the points with error bars are the experimental points. What you see, or what you're supposed to see, but maybe it's not very visible in this plot, is that every single point is within error bars. Okay, so these are actually pretty good precision experiments. Furthermore, in these experiments, we usefully entangle, we create volume law states with up to 48 qubits. At the time when we were doing these experiments, this was like world record. And on top of everything else, okay, now this is a bit ridiculous, talking to condensed matter physicists, but you can try and do, finite size collapse of these curves of, systems of up to 24, whatever, okay, we just do it for the heck of it. And we find that based on this collapse, we can estimate the critical point within error bars, okay, the exact is 0.91. And also there's a dynamical exponent that you can extract from this transition. And if you do the collapse correctly, you get, again, to within error bars of the exact value, which is 2. Okay. Again, this is to be taken with a grain of salt. This is not like any serious numerical person will tell you that you need probably 2400 here, not 24. Okay, but just to show that this data is consistent with what we expect. Okay, so now if I go back to the questions that I posed in the beginning, how to measure entanglement? Well, in this case, we have a system where entanglement maps exactly to an order parameter that is measurable. Okay, so we measured exactly the entanglement entropy in the system. We have an exact theory in the non-trivial limit of the experiment. So we can, again, the functional form or the order parameter, I can describe it exactly. I have a closed formula for it. Something that I didn't describe here is that we didn't have to do any post-selection. And I will comment on that perhaps in the question period. And then finally, what I showed is that compared to other approaches, this experiment is quote unquote scalable, right? So just to give you a reference, at the time when we were doing these experiments, I think our competitors were doing, like the Google people were doing like a whopping 12 qubits. Okay. So in a sense, we have addressed all of these questions. Okay, so just some comments that I already made. Basically, the StatMech here exactly describes the system in contrast with other theories of these transitions in the steady state that people have used, percolation or capillary flow or like other theories that are approximate. And we were able to extract the entanglement entropy for a volume law state. And a bunch of other things that are not important here. One comment that I would like to make is where we're going in the future. What is the follow-up to this? And so, okay, we started with a theoretical proposal. Then we showed that actually it works experimentally. And now what we want to do is, can we make it do anything useful? Okay. So suppose that I now want to evaluate the ground-state entropy of a classical spin model, but not the p-spin model that I showed here. Okay. It's a more complicated model. And for this, what I would do is, in this circuit, instead of starting with this all plus state, I would start with some other constrained subset of states, and then I would impose this circuit of this initially restricted state. And what I want to ask is, how many configurations are in this initial state? Okay. So you can imagine that it's an exponential number, but it's not 2 to the n. It's 2 to the alpha n with some alpha smaller than 1. Okay. And the question is, or the problem is, determine alpha. I give you a quantum state to make it even simpler. I give you a quantum state. I guarantee you that all the components of that state have the same amplitude. And I want you to tell me how many there are. Okay, so this is a counting problem. And counting problems in general are difficult to solve because, so if you imagine I give you such a state, what could you do? Well, you could measure it in the computational basis and ask, okay, how many measurements do I need to determine the number of components? Well, it's exponential, right? So here we have a protocol to do this approximately in an easy way, meaning with a linear number of operations. Okay, how would we do this? We would feed that state into our circuit and we would generate exactly this plot. And how would we determine the number of states? Well, what would happen in this graph, it would be that this transition would shift to the left by a certain amount here, and this amount would give us the count. Okay, so basically, the amount by which this shifts by gamma, okay, to the left, our count is 2 to the 1 minus gamma n. Okay, so if I can measure this shift, I can count the number of states, so I can evaluate these stat-mech partition functions using this methodology. In computer science, this is has a name. It's called Stockmeyer counting. So we're doing something like that here. Okay, so that's it. The conclusion is basically what I just told you. We generate these quantum states that display this non-analyticity of entanglement entropy as a function of measured qubits, and we have a theory, exact theory for this transition, and now we want to try and use it to do something useful. So that's it.
Thank you, Stefanos, for a very nice talk. It's time for questions. Any questions from the audience?
Yes, but I'm formulating.
Huh?
I'm thinking about what my question is.
All right. Well, you think maybe some question from the online audience?
I have a question.
Yes, please.
It seems like your quantum circuit is classically simulable. Can you comment on if you were to move away from that, would you still have this nice relation between the entanglement entropy and order parameter?
Yeah, great, thanks. So I said that I would comment on these red curves later. So now is the time that I comment on the red curves. So in the circuit here, on the left, the input state for the spins, the qubits representing the spins, which I call spin qubits, which is confusing, but anyway, the spin qubits is a uniform superposition of all states, right? So here the red curves instead show what would happen if I input a Haar random state. So what's a Haar random state? Is a completely random quantum state. So I take each amplitude is a random complex number, and then I normalize. Okay, now this is a state that is as hard as it gets to simulate classically. Okay, so now in this limit, the red curves that I'm showing here, and you can see it also in terms of the simulability. If I start from a state that is the old plus state, you notice the circuit is just C naughts, right? Because swaps can be decomposed as C naught gates. And so, moreover, each operator here is a stabilizer. Initial state is a stabilizer state. So this is a stabilizer circuit, is easily simulable. But if I change the input here and make it a Haar random state, now none of it is easily simulable. And this is reflected in this plot here, where for the random circuits, we can go up to 24. We could push it a bit further, but this is hard to simulate. Now, the experiments were done, again, for the simple initial state, the old plus. And the reason for that is that actually on these computers, it's hard to prepare these completely random states to reproduce this red curve here. So it's an experimental limitation that prevented us from doing that. But in principle, you could do it. And as this curve is supposed to show you, you expect to get the same result.
Thanks. I don't know if I can ask another question.
Yes, please go ahead.
Sure. How does the length of the width of your circuit scale with the system size?
Yeah, linearly.
Is it constant? Linearly, okay.
It's linearly. So both depth and width scale linear. Well, width scales linearly kind of by definition, right? It's your input. It's just that we have this alpha overhead. So for the maximum alpha you want to go to, in the naive way that I showed you, the width of the circuit scales as alpha n, where n is the number of spins. Now, in principle, what I could do would be to, I could use just one extra qubit for all of the parity constraints. So the width then would be just n plus 1. How? Well, I would thread this qubit here measure it, and then reset it, and reuse the same qubit to apply the second constraint. But the issue there is that you end up doing way more swap gates, right? So, and then these circuits actually, these machines, as I said, they're not the best. Actually, they're pretty crappy, and so you don't want to increase the depth too much. So there's a trade-off between width and depth, and you want to find like the optimal between the two, the optimum between the two. And then, as you can see, also the depth scales linearly. There's no, the depth of how many gates you apply in this case scales linearly. Is kind of like the diagonal of this, roughly the diagonal.
That's because it's the spins are all to all kind of coupled.
That's it. Yes, exactly.
Yeah.
So
Okay.
could I do this on planar graphs? If you could do this on planar graphs, then then this would change the depth of the circuit. And actually, the depth of the circuit, I kind of alluded to this when I was talking about all these experimental tricks, these rotations, and like the circuit rewriting, and what we do for error mitigation. We try to compactify the circuit as much as possible by rewriting gate equivalences. So using gate equivalences to rewrite the circuit to make it as shallow as possible.
I see. Thanks a lot.
Have you thought about your question?
Yeah, but it's too much. I'll ask after we get off.
Any questions? So this, can you comment on these tricks that you use here? Circuit rewriting.
Yeah.
Rotation,
So, okay, circuit rewriting. Circuit rewriting, what it means is if you look at the circuit again here, I'm applying C0 after C0 gate. Okay, so let me show you specifically this one gate that I put in this box. It's a C0 followed by a swap. A swap can be written as 3 C0s, one after the other. So, but it doesn't matter if you start with control target or target control. Okay. So what will happen if I would say for this swap I use the first qubit as target and the second as control. I would have one C0 this way, one the opposite way, one C0 this way, one the opposite way. Okay. But what if I do it the other way? I would have target control. I would have target control again. So these cancel out. And so then I would have just 2 swap gates. Furthermore, you can rewrite this matrix such that it has the same rank. If we pack it, you can rewrite this such that you pack it with ones. If you have a lot of ones, you get a lot of these cancellations. So your circuit effectively becomes shallower. Okay, so that's one trick. Furthermore, if you have an alpha greater than this alpha, if you have more interactions than you have qubits, you know that your rank can be at most n. So if your rank is n, that is equivalent to a square matrix, right? And so if you have more interactions than you have qubits, you can always kind of fold this matrix back to a square matrix. So that's another thing that we do, but it's equilogical. Nothing changes. It's exactly the same constraints, just expressed differently. Now, what else did I have here? Shot rotation. Okay, so I talked about post-selection, okay? And the idea there was I want to average the outcomes over the same measurement record, okay? But if I have a fully entangled state and each measurement outcome is equiprobable, well, it's exponentially unlikely in the number of measurements that I will get the same outcome. So if I measure these qubits and then I run the same thing and measure these qubits again, I would get a different outcome. And in fact, all of them are equiprobable. So it's 2 to the m outcomes, possible outcomes, each with the same probability. So 1 over 2 to the m. Now what we do in this case is the following. This thing here is also an error correcting code. these are the syndrome bits of this error correcting code. And this means that for every syndrome configuration, I can quote unquote correct the state to bring it to the zero syndrome sector, to the error-free sector. Okay. So by effecting error correction, whatever the outcome is here, I can always kind of gauge transform it to the same gauge. And so this means that now I can bring all of my measurements into the same sector. And now I can calculate the overlaps and the order parameter that I showed you. Okay. And then final trick, what was it? Error mitigation. Okay. Error mitigation in this case is the following. If I measure, in the end, in these circuits, we measure all of the qubits, okay? We don't measure partial. So we measure all of the qubits, and then we obtain a configuration, a spin configuration, and a corresponding parity configuration. So when we perform this measurement, now we can kind of like plug the key, put the key in the lock, right? So the parity configuration should correspond to the spin configuration and vice versa. If that is not true, then that's by definition an error, okay? We have detected an error, and if we have detected an error, we throw out the shot. Okay, so now the question becomes, how many shots do you keep actually in the end? And so this is what I've swept under the rug. And so now you are keeping me honest. So now I show you the proportion of good shots that we keep for different sizes, okay? And as a function of number of depth, basically circuit depth, okay? So this is the circuit depth. This is the 8 qubits. And this is how it evolves, okay? We have, for very shallow circuits, almost all of our shots are good. And then this goes down, and then we end up with some rate of getting good shots. Now let's double the system size. So it's basically order 1, okay? We need, for every one good shot, we do order 1 shots in this case. Here we need about 100. For every 100 shots, we get one good one. And when we scale up even more, so we triple this, okay? Now we need 10,000 shots to obtain one good one, okay? So this is in a sense an overhead that comes from the quality of the qubits. Okay, so what does this mean? It means that, well, at these depths, now the qubits decohere. So instead of getting a good shot, you get garbage. So.
Very good. If we don't have any other questions, we thank Stefanos one more time.
Thanks for the great talk.
Thanks for the questions.